Okay, so there is a clicker question after this one, and then we will look into much more difficult problem on this item 28.3. So this is more complex, and let's just read the problem first. In the next experiment, an equal arm balance beam will be used, as you can see it on the figure. Two forces will be applied to the beam, as shown below, and on the right side actually. One force F2 acts straight down, while the other F1 acts at an angle beta, as you can see it, to the horizontal. Okay, assuming the beam does not rotate, work along with the instructor to apply Newton's law in rotation form. Okay, so, and the goal is, I'm gonna show you a little bit of next step, is to find the, so using your results from the previous step, we will perform algebra to develop an equation for the ratio of the two force magnitudes, F1 over F2, okay? So we're gonna get a relation between those two using torque. Okay, so first of all, we know that the beam does not rotate, right? And that means, again, we are dealing with an equilibrium case, okay? This is important because that tells you alpha should be 0. That's what it means. Acceleration is 0. If you have a linear equilibrium, then you have A to be 0. If you have a rotational equilibrium, then you have alpha to be 0. If you have a equilibrium for, like, in general, then both of those accelerations are 0. Okay, so we have a rotational equilibrium and also translational, but we are focusing on the rotation part. Okay, so figure is a little complicated, so let's just look into this on a separate page. I copied the figure here. So what we're gonna do is, again, let's apply our torque relation. So we know that sum of torque equals to I alpha, right? And again, torque is a vector, alpha is a vector, but we know that alpha is 0 because it's in equilibrium. That means sum of torques are going to be 0. And we are going to think about how many torques we have, and we'll apply this equation. So when we apply it, torque in general is Rf. So let's just apply it, and let me just write it in the vector form first. R cross F, right? So we are going to consider this for individual forces. Okay, so we have two forces, F1 and F2. Here, this is beta, and F2 is straight down. H is, you can see that given H from the pivot point to the vertical distance to the force points, L1 and L2 are horizontal distances from the pivot to the force points. Okay, since we are going to apply the torque in cross product, what I want to do first is write those vectors. What is R1? Okay, so when I write R1, I'm going to focus on this triangle here. That's a right triangle. And H and L1 are the components of R1. Okay, another thing that I need to focus is, where is my coordinate system? We choose the pivot point to be the kind of the origin, right? You can see that this is X, right? And this is Y direction. So pivot point is origin. Below Y-axis is negative. To the left of X-axis is negative. So that would mean both the H and L1 are negative. So I'm writing R1 vector in terms of those components. L1 is along the X direction, so it's going to be negative L1 I hat, okay, and negative H J hat. If you have a trouble seeing any of those, pause the video and then double check it. Okay, I hope that this is clear. So I'm writing R1 in unit vector notation using its components, using the triangle that I see there. And I'm going to do the same thing for R2 now. Now I'm going to focus on this triangle here. So let's write down R2. So for this one, R2 is the hypo. Again, H and L2 are the components. H is along y direction, L2 is along the x direction, and you can see that L2 is positive because on the right side of the origin, and we're gonna have positive L2 I hat then, and H is still negative, right, because it's below the origin. It's gonna be negative H J hat. Okay, so now what we need to do is find the torque due to 1. And what is that? It's going to be R1 cross F1. And we'll do the same thing for torque 2 as well. Okay, so what do we have here? Let's just write that down. But before writing down, let's also get those force equations as well. I'm going to use red. So this is R1. What is F1? Let's split the components for F1 as well. So we will have two components, right? These two. Tangential and radial. And what are they? For the x component, again, you can see that x is pointing to the negative direction. So it's going to be negative F1. Since this is the angle, it's adjacent to that component. It's going to be cosine beta. And we have another negative component because it's going down. It's going to be F1. And the angle is opposite, so we are going to take sine function for that. What did I miss? I'm trying to write a vector, but on the right side I have no vectors, right? I need to put those I hats and j hats. Okay, let's do the same thing for F2. For F2, it only has y component, so it's like 0 I hat, and it's downward, so it's negative. The whole thing is along the y direction, so it's going to be F2 and j hat. Okay, so now let's focus on the torque 1. So what we need to do is kind of focus on the first line. So we're going to get these two, right? So this goes in there and then this goes in there. Actually, let's do it this way. This is R1, this is F1. Let's put them in there and then let's see what we are getting. Let's draw with the green. So negative L1 I hat minus H J hat. You gotta multiply them with a cross product, and negative F1 cosine beta I hat, negative F1 sine beta J hat. Okay. So when you do a cross product, again, it's really important that you show what type of product this is, because if it's a dot product, your answer is totally different. So it's a cross product, we have to show that. And next step is to distribute this, right? So you're going to do the first term with the first, and then the second, and then the second term with the first, and the second to second. So there are 4 terms. But if you recall, there is cross product, non-zero cross product, only between the unit vectors which are different, right? If you're doing I cross I, it's going to be 0. Okay, or j cross j, k cross k, they are all 0. So keeping that in mind, I already know that when I multiply first term with the first term, I'm gonna get a 0. But I'm just gonna write it down just so you can see it. So torque 1 becomes negative. So the first term is negative, negative becomes positive. L1 from the first term, and then F1 cosine beta, but this is I cross I. Okay, I'm going to write all 4 terms so we can really analyze this problem. And now the first term and the second term. I'm doing a cross product between them, and they're also both negative, and that means I'm just going to have a positive value again. So first term is L1. I'm looking at the coefficients of I hats and j hats, okay? And j hat has a coefficient of F1 sine beta. And what do I have as a cross product? It is I cross j. I already thought about the sign, so they're both positive because you're multiplying 2 negatives. Okay, same thing. The second term for R1 and the first term in F1, let's multiply them. They're again negative to negative, so it will give me positive. First term has H, second term has F1 cosine beta, And what is this? J cross I. Next is the last two terms. So we are doing the y component of R1 and y component F2. Again, both negative. It will give us positive value H for R1, R1y basically, and F1y is F1 sine beta. So what do we multiply in vectors? It's J cross J. Right? And let's think about what we know. I cross I and J cross J are 0 because this is a cross product. They point the same direction. The angle between them is simply 0. Sine 0 will give you 0. Okay? And I cross J hat and J cross I hat. I cross J hat is going to give you, we've done this before in the unit vector notation, this is going to give you positive K hat. But what about J cross I? If you recall, I cross J and J cross I are not the same thing. They're going to be opposite to each other, so this is going to be negative K hat. Okay? In the next video, we're going to just simplify it and put things together.